Welcome to another installment of our Grasp on Robotics seminar series. So I am Ani Shear. I'm the faculty host for today's presenter. And joining me are our two PhD student panelists, Tori Edwards and Ben Schaefer. So a quick thing for you, those of you that are joining us over Zoom, remember to submit your questions using the Q&A button at the bottom of your screen. These will be answered during the Q&A panel at the end of the talk. For those of us who are here, you will have an opportunity, right, to ask your questions. Just make sure to wait for Tori or Ben to bring the microphone to you so everyone online can hear the question. So without further ado, it is my great pleasure to present Dr. Kristi Morgansen from the University of Washington. So Professor Morgansen is the Boeing Agvet Endowed Chair for Excellence in Engineering in the University of Washington College of Engineering. She's also the department chair for the Department of Aeronautics and Astronautics. So she does really cool work, and actually, so she does everything from nonlinear control to dynamical systems, and then autonomous systems, both aerial, underwater, as well as space stuff, super cool things. So her work has been applied to a wide range of traditional and bio-inspired sort of aerial as well as underwater autonomous vehicles. So I do not have the time to list all of Professor Morgansen's accomplishments, but I'm just going to sort of highlight a few things. So she's co-founder and co-director of UW Space Policy and Research Center. She's also the director of the Washington NASA Space Grant Consortium. And she's also a fellow of AIAA, a member of the Washington State Academy of Sciences, and a member of the Department of Air Force Scientific Advisory Board. So please join me in giving a warm welcome to Professor Kristi Morgansen. Thank you.
All right, well, it's really my pleasure to be here today. I love to do the research part of my life whenever possible. Some of those other tasks involve a lot of HR, and that's not necessarily a fun thing, but I think it's very important. Service is very important. So if you want a place to run well, I feel like you should contribute. So I'm going to put my plug in there. Everybody should do service. All right, but what I'm going to talk about today is some of the work that we do in my group around sensing and actuation. And so I am a nonlinear control theorist, sort of by training and by inclination. But I love to see both the mathematics of things and the application working together. And I'll talk a bunch about the different tools that we use today, as well as applications of those tools. So there will be some math, but I'll try and make it accessible for people who are not so much on the mathematical side, and then also show applications in a number of places where we've used the tools. So here's a few of the places where we've used the kinds of things we're working on. I'll talk today a bit about this fun creature that's in the upper left. That'll be sort of later on in the talk. It's a SALP, so it's an underwater creature. And we're looking at doing some soft underwater robots based on how they function. The second one here is a hawk moth. They're actually about yay big. They're a pretty beefy sized moth. I've done work with biologists who work with those for a number of years. And then I'll not talk too much about the other two pieces up here, but we do things like deconfliction. So how do you keep things from running into each other? Working with schooling fish is stuff I've done in the past. I'm not going to talk so much about this particular application here, but we use the tools I'm going to talk about for trying to track down, how many people do you need to test in different villages. This is actually before the pandemic. It was with Ebola. To know that you've got a good sense of how a disease is spreading. I will talk a bit about some neural network applications with vision it's actually sort of based a little bit on classification. I'm not going to talk too much about security here, but there is some network applications for these tools. So mostly what I'm going to be talking about is observability, which is how do you invert information from sensors, knowing system model in order to get information about the state. Usually you're trying to get the most information. In the security application, you're actually trying to prevent information from flowing. Okay, so here's kind of a high level picture of some of the pieces that I'll talk about today and some of the general principles. And I'll talk through the various pieces here as we go, but if you're familiar with such things, the separation principle in linear systems tells you don't have to pay attention to how a system is moving or how the control is acting in order to do the sensing. There's actually things that happen in nonlinear systems where that's not necessarily the case, and that's something we leverage. And then how do you balance analysis and synthesis against computation and testing? So in particular, I'll be talking about these 4 pieces here. So analysis versus empirical tools, because sometimes you can't get very far with system complexity in terms of doing analysis. And then how the motion and sensing can interplay against each other. So I'm trying something a little bit different on my slides today. I decided to throw this in last night. So I'm going to use these little diagrams here in the corner of slides to kind of talk to emphasize like which pieces I'm talking about at a given time. So hopefully that'll help with some clarity there. And then toward the end, I'll talk a bit about how we can get into some stochastic pieces of this work. Okay, so high level piece here is what is observability? So that's going to be the linchpin for everything I'm talking about today. So the general idea is this is our standard block diagram, feedback loop for a system. So you've got whatever dynamics model of your system right here. The state is going to come out of that in some sense. There may be disturbances coming in. So you've got your controller you're applying to your system. So disturbances can come into that, go into the system. There may be uncertainty in the system. When you do measurements down here, there's noise that comes into that. And then you get your measurements out. And then from those measurements, you apply an estimator or a filter or some sort of tool along those lines in order to extract back out the states. So that X hat is the estimate of your state. And then that sigma is the error covariance. Okay, and so that sigma is very important because it tells you how well do you think you know that estimate. And because of noise, like you're never going to know that estimate exactly. And because like usually your measurements, there's not like a direct inversion. And so that error covariance, how tight that is, will go back. And as you control your system relative to what you want it to do, you were going to try and when we design controllers for robustness, we're trying to be able to handle as much uncertainty as we can. And if you have eaten up a whole bunch of your capability with a very messy estimator, so your sigma, your error covariance is very broad, you're going to eat into your uncertainty. And so at a high level, that's one of the things that we're interested in managing in our systems with our tools. Like how can you do best on your estimation and your measurements so that you can leave as much margin for robustness in your controller as possible. And I'll just say at the beginning here, we don't have that answer explicitly written out yet, but I just want to kind of give that as a motivational piece here. Okay, so what we have in this model, kind of boiling it down, when you look at your measurement function here and kind of look at the mathematical relationship of the pieces, your measurements Y are going to be this in general, are going to be this nonlinear function of the states of your system, as well as the control. And what we want to be able to do when we're talking about observability is answer the question of whether or not you can extract out that state from this inverse relationship of your measurements and your control, because one assumes that you know the control because you got to pick it. And the measurements are things you get because you measured them. Okay, so how does this work? So I'm going to go through some of the mathematical pieces here. And so this is an analysis thing, and this is just looking at the sensing side of it. So that's why the little bubbles are colored over there. Again, it's the first time I've tried little bubbles. We'll see how it works. So in a linear system, this is your standard continuous time linear model here, AX plus BU, XI equals AX plus BU, and Y equals CX. And one way of thinking about observability in these systems is if you start taking derivatives of your measurement over here, so these numbers here represent the number of derivatives you've taken, and just write out what these equations look like. So the first one's just Y equals CX. And so this X is the piece that we're going to try and extract out of the system. Take a bunch of derivatives, gather up all of the coefficients of X, and then shove all the other stuff off into this vector on the right. And if you notice here, all the things in this right piece, we know all these things, assuming that you had some idea what your model was at the beginning and that you chose the control. And then we also assume we know the measurements because we measured them and you took derivatives. So if you had to like do that numerically, that is totally fine. And we assume we know the C and CA and all of that there. So the one thing we don't know is the X. And so observability in linear systems, regardless of all the different tools that you may have seen, kind of boils down to this in a certain sense. So those pieces are known. These things are, we assume, known. We assume this is known. And so then we just want to know, can you invert this relationship? So you can subtract off this vector on the right from the left. And then it comes down to, does this matrix here have full rank? Because if it's square, you might be able to invert it, but usually it's not square. So all of the pieces there, that particular one, nothing here depends on knowledge or is going to be affected by whether or not the system's controlled in a particular way, because you're just subtracting that piece off. So when we talk about linear systems, there's what's called the separation principle, that how it's controlled doesn't have any impact on whether or not you're going to be able to extract the states out of the measurements. Okay, so it's a little bit different in nonlinear systems. And so this is where, I've got that other bubble colored in because the control may matter. So if you write down dynamics similar way as with the linear system, except now I'm going to frame it a little bit differently here. So this is like the AX in a linear system. This is called the drift in a nonlinear system. And then these pieces over here are the controls. This is like BU if you pull it apart in similar structure, except that the elements of what would have been your B matrix in the linear system, they may be state dependent. They may also be time dependent. And so you can break apart these pieces here. Often you'll see it written this way, or you can lump them all together into one just big dynamical systems vector. And then you're going to have measurements. The measurements are often going to be state dependent. So I think like a good example of this is like in a robotic system, we often have sensors on board and they're actually getting body fixed measurements because you've got like a camera on board. And so that's getting measurements relative to the motion of the system. And so that is going to be a function of the state. More broadly speaking. And so if you go through, as with the linear systems, a similar process of taking these time derivatives of the measurements, you'll get a structure that looks like this vector here. So this is just taking time derivatives, and then it works out to look like this when you do your full derivative. If you then write this in terms of this function here, this f, then you can rewrite these. This is just a mathematical notation change here. These are technically called Lie derivatives. They're directional derivatives, but you can also just think of them as being these derivatives over here. This, if we now call this that function g of x and u, because this whole piece right here is going to be a function of the states and often a function of the controls, that is not necessarily going to be the same vector that you get from doing these derivatives if you set the controls to 0. So this right here, notice the difference here is this is an F naught, which means the controls are not in there. They're set to 0 versus this. And so in these nonlinear systems, while the pieces on the left are known, this relationship between the outputs and the states can end up being very highly coupled and be a function of the controls. So how that system moves may affect whether or not you even can invert the relationship. Whether, I mean, and when I talk about inverting the relationship, ideal world, like you'd be able to actually find an inverse for this functional relationship. But in general, the best you're going to be able to do is like a local, like do a Jacobian locally about a point and get a local inversion. But what do you do when those controls factor in there? It gets much more complex to figure out not only like how do you invert that relationship, but what are the best controls to make that work? Okay, so now, going back to that first diagram, we can look at, there's some tools around like, really it boils down to when you locally look at that function at some point, take a Jacobian of it. And if the rank locally is full rank, then you're good to go and you can invert it. So that's boiled down a whole lot of math into that. So let's see that a little bit in action. So I'm not showing like all the calculations of the different ways of calculating that local representation. I'm just going to show you some examples of it here. So one that we actually can do the analysis on, which again, back to my bubbles, that's why I've got the analysis and the motion one in here. If you look at a very simple model of a drone. So this one here is the Aerosonde. It was the first autonomous vehicle that flew across the Atlantic. It went from Canada over to Scotland back in the 90s. And it had, no joke, like the equivalent of a lawnmower's worth of gasoline in it. And very seriously, like I think they sent like 5 of them and 2 of them made it, which I think is like mind boggling that actually worked. particularly since the sensors they had on board, they had differential GPS, but they didn't have wind speed sensors. So, got a GPS sensor on there, but you have no idea what the winds are doing. And this thing is small and it's like going across the Atlantic. I think they did it when it was not like awful bad weather, but still. So the way that if you stop and think about it, the way that you can figure out doing course correction from the wind is you can do these sweeping motions and get like some idea of where the wind pushed you, okay? So those sweeping motions are in effect this very need for doing motion in order to get observability of the full state. And so if your full state is, just thinking of it in the plane, although you can do it higher dimension, your position, your heading, and then the direction of the wind, the X and Y, lateral, longitudinal wind direction, put all that into a model, so a 5-state model, which is about as simple as it's going to get. Write down just very simple dynamics so you can control velocity of the vehicle, and then the heading. That's basically what you get with a drone of that type. And then sense just the position. You can do everything with that as long as you're making those motions. But if you don't change your heading, you're not going to be able to lock on to both of the wind directions, both the lateral, longitudinal. But if you make these S turns, and you don't even have to do that much of it, you lock on very tightly, which is, they did this without me doing the math, but I thought it was great to go back and do the math, and it worked. It was lovely. So that's a really, I think, good example of how this nonlinear observability tool works. You can also build on top of this, and I'll talk a little bit about this, doing some optimization of, not so much on the motions, we haven't really done that, that's hard. But what sensors should you use? How do you tighten things up? Where should you put them so you make this locking on of the estimation as quick and tight as possible? Okay, so some of the things that come up though, with this tool. So that up till there, it's pretty much analytical tools. I swept a whole lot under the rug about how do you even do these calculations. And that one example I gave you was a 5-state system. And even with that one, it gets pretty complicated to do the analytical math on it. Real systems are not that easy. So the two I'm going to show here, and I'll talk about the ways that we're looking at handling each of these. The one on the left is talking about analyticity. So those models that I showed were differential equation-based models. And in order to use the tools, you have to be able to take derivatives of your system and evaluate those derivatives at the points of interest. In a lot of systems, you can't do that. So in this one here, I mean, this is completely something different. This is a classification problem where you've got, people or cars moving around or both, and you're trying to figure out what's where. Like that is not usually written out as a differential equation or anything of that type. And so trying to use these tools, which actually do have application here, where you're trying to extract out from this camera image, what are all the objects, that particular observability tool won't work. Just it's not built to. And then there's complexity. So if we get beyond like a sort of simple set of those kinds of descriptions of a system, what do you do? And I will talk more about this one here. So this is a hawk moth flying around. And what we've looked at with biologists is they have strain sensors built into the wings, like 200 of them in each wing. Can you get pose information from those sensors? Writing down the dynamics on that's really hard. Okay, so what do we do? So one thing you can do is do a local linearization about a nominal trajectory and then evaluate that local linear system. And so this is an analytical piece right here. So all of this you may have seen in a class that you took on control theory. The parts I want to point out, so this is what you get. So you have this nominal trajectory here. And this is a bad notation thing. Often we refer to as a system as a sigma, but that's not the same sigma as in the error covariance. But so you get this linear system here. It's often time varying because when you linearize about a moving trajectory, you often end up with a linear time varying system. It turns out that your nonlinear system is going to be locally observable about that trajectory if this matrix W down here, if you look at the output energy of your system, so 2 norm of your measurement function, it expresses out like this in a linear system format. And so this whole integral here in the middle, which is from your start time until when you stop taking measurements, and then you're going to extract out the state at time 0. If that integral, which is a matrix, if it's full rank, that's called the observability gramian. If it's full rank, then your system is locally observable. And so that's an analytical result for a local nonlinear observability. It turns out that you can re-express this whole gramian here as a sensitivity function. So the sensitivity of your measurement relative to that initial state. which is really what we care about. You think about that, I want everyone to think about that as if your system's observable, it's going to be very sensitive to that initial state, okay? Meaning that like you change the state, you will change your understanding of the initial condition. If it's not sensitive to it, you can make that initial state whatever you want, and you're going to get the same output. So that means unobservable because multiple things are giving you the same answer. So we want to have high sensitivity here in order for our system to be well observable. But having framed it in this particular mathematical structure, we can actually construct this sensitivity using numerical tools and then actually get a version of this gramian using simulation rather than having to calculate it analytically. It's a trade-off between having to do a whole lot of math that you might not be able to get a solution for with having to run a whole bunch of simulations. So, no free lunch anywhere, but it does make progress. So and these are tools like this empirical gramian was developed by other people. Some of it was from doing model reduction. So Sanjay Lal and company did some stuff back a ways. And then Art Krenner also did some of the underpinning development here. So we didn't do this. We've built some stuff on top of it. I just want to make sure people understand it. So what you can do is with your nonlinear system, you start with that nominal trajectory, and then you perturb your initial conditions plus or minus epsilon, so a little bit in each of the basis directions. That's going to give you some perturbed trajectories. And then you write down what is the delta in each of the measurements from those perturbations. And you can form a matrix out of that. And that gives you an approximation as your epsilon gets small, it gets close to accurate of the gramian of your system. And then now you've got something you can now do checks on rank of that matrix. Okay, and so this, again, Krenner did the result here. We have built on top of that with other tools. And so, sorry, this is actually our result. But so the initial stuff came from Krenner, and then we started putting some foundational pieces on it, including like adding those controls back in. Okay, now really important point here, and this is something that is driving a lot of what we do, is if you remember back when I said that error covariance is very important for maintaining as much robustness, control robustness in your system as you can. Well, we know that the error covariance of your system is going to be bounded by the Fisher information matrix. That's a well-known thing. It also turns out that in a linear system with Gaussian noise, you can bound the Fisher information matrix with the observability matrix, and in particular with the gramian here. And so that's super handy. And if you think about it, it makes sense. The better your sensing is, the better your estimation is going to be, regardless of what kind of estimator you use. So this is all independent of, are you using a Kalman filter, a particle filter, a Bayesian filter, whatever. All of it gets better if you have better sensing. And so we're putting some numbers on that. It's not equal to it, no. And so another thing to know here, so the reason that this is written this way is, if you think about it, Fisher information is done. So the question was, why is it not that the Fisher information matrix is equal to the thing I have on the right, on the observability gramian, right? So observability, and this point will be on another slide, but I think it's good to bring it up here. Observability, all these tools I've shown so far are for deterministic systems. And the Fisher information matrix and estimation inherently are done for systems with noise. And so they can't be equal, because the Fisher information is specifically for a stochastic system. You can, yeah, so the observability of the stochastic system.
Same as the observability of the non-stochastic system.
No, actually it's not, and I'll show a result about that. If you're going to do observability of a stochastic system, you have to do a whole different framework of observability. What people do, if you talk about, like often when people talk about observability of a stochastic system, they have hacked off the noise and are only talking about doing the observability on the deterministic part.
Okay.
Unless you have some other information, which I would love to hear, because we've explored a lot in terms of what is out there in terms of tools for stochastic systems, but there's not a lot. But I hear you. But yeah, I mean, regardless, and often it might be that they're equal. But so if you look here, so that R inverse that's right there, that's the measurement noise matrix. And so the Fisher information is bounded below, and this is the reference of where that's all proven, is bounded by the minimum singular value of the inverse of the measurement noise multiplied against a particular function of the observability gramian. And again, this result is just for the linear systems, but if you think about it, we just haven't found the right math to show a similar result for the nonlinear system, but so locally with a linearization of the nonlinear system, you'd get similar kind of behavior.
You mentioned empirical observability. I come from the old school. Where is the calibration come from? Or do you ignore calibration?
And what do you mean by calibration?
Well, look, that box, nonlinear simulation,
Yeah.
is a transducer,
Yes.
okay?
Yeah.
And has some physical properties.
Yes.
The transformation function, but it also has the noise signal
Oh,
to
sure,
noise
sure, sure.
ratio and sensitivity and all
Yes.
the stuff that in the old school we
You had to
pay a
take
lot
into
of
account.
attention. And now
Yes.
I am worried that it's kind of
Yeah.
looked
Yeah.
over.
Yeah, well, so to a certain extent it is. So in these tools, as they were initially developed, and I will say, yes, that is absolutely something that is still an open piece. So the tools that were developed were done assuming, and again, in this case, it is assuming that there's no noise. So this particular, when I say nonlinear simulation up there, what proofs we have on the results are for a deterministic system that you know exactly what those dynamics are. So there isn't actually in that case a need to, or there's an assumption that you have all of that done, that the calibration has all been done. I will, again, I'll talk about the stochastic framing in a little bit, but that does factor into like, how do these tools generalize to the more applied framework? But most of what is out there right now assumes that you have exact information going in there.
Data is
Right. Yes. Yeah. So I'll talk about that a little bit. I've got some neural network stuff. Yeah. Yeah. Yes, absolutely. Yeah. So I'll talk a little bit about that in a particular application. I actually did take a lot of my slides out because I was like, I know I never have enough time to get down in these rabbit holes. Okay, I'm gonna have to and I didn't write anything down. Okay, I'm gonna have to remember that. Okay. Anyway, so going back to this, I'm just gonna reference this picture one more time. So what we have been looking at is knowing that in a certain sense, observability is a bound on your error covariance. What can we do to tighten everything up and get the best results possible? And so best, of course, kind of brings to mind an optimization challenge, which is direction we go. I will say there are lots of open questions here. I think there's one of the things I'm hoping to get out of my visit here is some opportunities for collaboration, because I think there's just a lot of different directions we can still go with the things that we've been doing here. And so one of them would be, we have not yet quantified in any way, like if we can, in whatever application, that relationship between the observability back to something precise about robustness. Like if we knew something about particular structure of your observability, then we could say something in some particular example about the robustness margin relationship. That's the dream, particularly since in most of the cases here, like that control is going to matter. Okay, so some of the questions that we look at, and I'll talk about applications and results we have for a number of these. So what motions are necessary for observability? So I talked about that a little bit at the beginning, like with that drone example. The ones I'm going to talk about mostly here next are what sets of sensors is best. So a lot of the applications we look at, we have a lot of sensors. Like that hawk moth, there's 200 strain sensors on the wings, each wing. Which ones should we use? What's the best position of them? How many? And then there are metrics, because when we're going to do some optimization on this, there are different metrics that have different results. And then I just mentioned the controller robustness, and then how much can you determine analytically versus empirically, which I think goes back to your question about being careful about those boundaries of what you're assuming you know exactly and what you just don't. Okay, so here's that nonlinear framing again. So this is a nonlinear system, so our drift, our control vector fields, measurements, and now I've added in here some S's, and these are switches. So this is assuming you have lots and lots of sensors in your system. I'm going to put a multiplier on each of them, which often is just a binary thing, which is on or off. In some cases, we look at it as multiple options where it could be different types of sensors. And so depending on what the number is, it determines which sensor type you use, whether it's like strain or bending or shear or bending in terms of strain. And then we do an optimization. I'll talk about which kinds of metrics we've looked at. Looking to those sensors have to be in a particular set and the measurements have to be a particular type. And then what do you do? So these are dynamics, the measurements, we've got these switches. We put some metrics on things, the constraints, and then what ends up happening, of course, this is non-convex. It's constraints, we add some more, usually we relax it in some way or another, so we can try and convexify it. Often it ends up being something where we do online learning or nonlinear programming to get a solution out of it, so it's numerical. And then here's a bit about some of the metrics we've looked at. We are not the only ones looking at these, but depending on what kind of thing you look at, you're going to get a different answer. So some of it you might look at like the minimum eigenvalue of the observability gramian, which is going to maximize your lambda min inverse maximizes the estimation uncertainty. You can do minimum estimation uncertainty. Look at the whole shape of that ellipsoid, the volume of it, the average, like there are different things. And so I think it's still very much an open question about which one's best. I mean, I will say what we have often done is pick one that seems to make sense and look at the results at the end. So open territory there. Okay, so let's look at an example of this. This is one where we have done some of this work looking at, again, this hawk moth. And the question was, can we get body rotation rate out of strain information from the wings instead of using like a gyroscope? Because I do not believe that insects have gyroscopes on board. And it has implications for like engineered systems, because if we could come up with an ability to use much simpler sensors, then A, the cost goes down because the sensors aren't as expensive. If you're using smaller ones, you can have a lot more of them and have more redundancy in the sensing. And so the way that this is using that empirical approach. So what we did was we had like actual physical trajectories that were measured by biologists. I'm not a biologist, I work with biologists. So they actually collected information about a trajectory that the moth was flying. We took that as well as the material properties for the insect, did a simple finite element model of the wings and quasi-steady aerodynamics to make a model for this system, and then ran that through the simulation, did this 2n times, so perturbed the initial conditions on, excuse me, on that insect 2n times, and then looked at the results. And so we did this optimization in a number of different ways. We actually did it on a hawk moth and then a honeybee and a fruit fly, and looked at where, I think it was usually like 20 strain sensors out of the 200, where should they be? And so the blue boxes on here are where the actual strain sensors, campaniform sensillae, are on the wing. So biologists went in and did that. I believe it was it was probably undergraduates who did that, maybe graduate students. Good times. And so we constrained the places where our sensors could be in this model to be only at those places where there were blue boxes. And then we said, okay, well, assume you could have either shear or bending strain sensors. Where should they be? And I think not surprisingly, we end up with a lot of bending ones down at the root of the wing, because that's where you're getting a bunch of that kind of motion. But you end up with like some of the shear ones out at the wingtip. And depending on what kind of FEA model you use for your wing, so the top one was just a cantilever plate. This one was actually, we digitized a wing and shoved that through an FEA thing. So the placement of the sensors ends up a little bit different. So in the top one, they ended up on the edge of the end of the wing. And then this one in the FEA, like a more accurate model of the wing, it ended up on the front edge. And then doing similar things with the honeybee and the Drosophila. And these things are like orders of magnitude in size difference. So they are very different insects, but the placement in like sort of along the leading edge here on the Drosophila, which is like, a fruit fly is itsy tiny relative to most things, including a hawk moth. You end up with some similarities. It's still plenty of open territory to run there, but that's some of the kind of results that we are able to get out from these tools.
Sorry, so how did you choose? Can you talk a little bit more about the optimal sensor placement? Is this just you have a list of candidate locations?
Yeah.
And then you're just looking for brute force the best one, or is there a acquisition function that you're going after?
Yeah, so we set it up like this. And so we put switches, like, so we had those 200 blue boxes on the wing as the potential locations. And so we set up the whole thing where each of those, you can actually break up the observability gramian into a sum of pieces, one for each of the sensors. And so you add all that up, and so you get this big cost function. And I will be honest, I don't remember off the top of my head which of these metrics we used in there, but I think we tried probably all of them. So it was probably like log det, I think was maybe the one that we used. So looking at the volume of the estimation uncertainty, so minimizing that. And then ran that optimization. So ran it as a numerical optimization, and said what was the best answer for like 20. Like if we limited the number of sensors to 20, which I think is the correct number there, where should they be and which type should they be?
And is this done? So in some ways, this is like active learning versus batch base
Yeah.
opt versus batch base opt. So
Yeah, you can.
does this give you a single placement and now you're looking for a second one? So are you
No,
getting
it does
the
it all at
information
once.
in aggregate?
It does it in aggregate. So yeah, so effectively what it does is like you add up like, so again, so like for each of the sensors, like you can break up the observability gramian into a sum of observability gramians, one for each sensor. And so it's basically saying which of those are the 20 best that give you the most, like the best rank result. And so it's done all at once.
Got it. Thank you.
Yeah. Although technically, I mean, you could just like, order them in size and then you could just, however many. Yeah. Yeah, but there's lots of stuff that can be done there. Okay, so that's the using sensors on a wing. This is a project that we have been doing with Boeing. So this is the Eco Demonstrator. It's a MAX 9 vehicle. And so it flew, the data all came from a couple of years ago. So I'm not able to show the actual data. I'm just going to talk you through what we did and kind of what it looks like. So here, what we're interested in is putting IMUs into an airplane or any kind of vehicle, any kind of system, and saying, can we extract out information about the inertial properties of the system? So we're adding some additional states into the position and orientation of the vehicle to include center of mass, value of the mass, and moments of inertia. And the reason that that's of interest is, I think I keep bumping things here, sorry about that. If you want to determine in real time things like icing, aircraft icing is a very, very difficult thing to identify. So we're looking at, is there information coming in where if you're like in real time tracking the inertial properties of the system, can you get information that something happens at the time of icing getting to a bad place where you could identify it? Is it possible to identify asymmetric fuel burn in the vehicle? You can also potentially use it for sensor fault detection, since I'm not sure how many people are familiar with such things, but aircraft certification requires that you have multiple sensors running, usually of different types and structures, to get the same piece of information. I think they require like 3, redundancy of 3 in most kinds of applications, so that you know that your information is correct. So aircraft are in fact very complicated things, and their flight control systems are very, very complicated. So what we did, just to generalize this, so it's not actually the Boeing data, we took an airplane model, your basic rigid body. You could make it whatever shape you want. It's a basic rigid body, and looked at where you put the sensors. Can you get that inertial information out of doing sensing of acceleration, translational acceleration, and angular velocity from an IMU? And we just put Raspberry Pis into the airplane. So it was intentionally low tech. Like, what can you buy off Amazon? We actually had to get slightly higher tech ones because of the chip shortage. So we had to go with a fancier one that was available. Okay, so short version here is that you can get the motion state. So that, by which I mean, like, we don't really care about the position, but the velocity and the angular velocity, you can get all that with one of those sensors, one IMU, and no motion control, like no specific motion control, as long as the angular velocity of the system in the plane, this was just done in the plane, as long as that's not 0. And I didn't show all the exciting data here, but like when we were initially doing these results, and I just remember like a meeting where I was talking with our Boeing people, and we were looking at the actual magnitude of the omega Y, and we hadn't stopped and thought for a moment about like physically what was happening to the airplane, but that puppy was spinning nose over tail. And we're kind of like, we should probably look at like how small can the angular velocity be? Because you cannot do that on a commercial airplane. So we actually got it down to, if you look at the scale here, I mean, this is done like with force and moment, but the like the force here is like 10 to the 5th here, but it actually comes out being like a very small angular velocity. And so this is the actual path that the vehicle would take. So it's kind of like a takeoff maneuver. So you're going and you do a pitch up. And so that was actually sufficient, like in that time frame of when that's happening, that this would work. So we did get it to a place where we felt like it wouldn't upset passengers too much. Okay, so what I want to show here, sorry, this is a little bit of an eye chart, but I wanted to show these data here. So the stuff on the left, so this is basically, it's a comparison of what happens with 2 different types of filters. So we've got an extended Kalman filter, which is really the most basic kind of filter you can use. It's used a lot because it is a low computation kind of thing. Just a linearization of a Kalman filter. So you linearize your model locally and then do a Kalman filter. But it is susceptible to any kind of nonlinearities in your system. If you meander too far off of your linearization condition, it diverges, which is what you see over here. These are the, so it's the sort of the physical states over there, and then the inertial states here. So like we were doing pretty well with, in some cases with the, pitch and the velocity. So the green is the true value here. But we did an unscented Kalman filter, which is more of a nonlinear filter. That did a lot better, but it is a higher computational cost than the EKF. And then over here, you can kind of see the EKF, even though like the results say as long as you get that pitch maneuver, it's all good. Once you were away from that pitch maneuver, it very quickly diverged for the values. Like we could get like some of it, but not all of it. So like the mass we could lock onto, and one of the locations of the mass, like the Z location we could get, but then not so well on the others, or you could do various things. So turns out though, that was with one sensor. And so we looked at sensor location. So so this is now just the UKF. And so individual sensors, they would all stabilize if you did one of them, and they would do better down here around that pitch maneuver. But if you could take multiple of them, and in particular locations, that's what's showing here is like this solid line where we did many sensors together, you can actually start locking in on the true values. I'm scooting a whole lot of math under the rug there. But, and I will acknowledge, I did not show the 3 sigma bounds here because it was already an eye chart. But things do converge as long as you put in a reasonable number of sensors and they're in a decent number of locations. So what we're doing with that now is switching to a different system here, going back to that underwater creature called a SALP. So this right here is a picture of an actual SALP from one of our biology colleagues. This is a project in collaboration with Oregon State and University of Oregon. So these animals are super cool. So they're individuals. A little zooid is, I'm not sure how big they are, but imagine it's this big. They have a single jet. And then what they do is they connect themselves together into chains, and they get these interesting structures that they form, and then they move around in the water. And so the interest in using these is to build soft underwater robots that can do grasping kinds of tasks and maneuvering tasks underwater, and that these will be able to connect and disconnect. So if you look at this, coming up with inertial properties of something like that is non-trivial. And if they're connecting and disconnecting, they're going to be dynamic in their inertia. So we're working on applying that tool from the prior study into here. So we're just still working on getting our dynamics sorted out, and we're generalizing it into a planar robot here that's got multi-links. And so we should soon have some results on that. But I wanted to show that application as something that is bringing together all these parts, and that's one of the things we're working on right now. Okay, and then I want to switch now to what happens when you've got millions of sensors, which is how I'm going to frame like vision. So one of the things we've looked at is using vision to sense pose. And so this, and I'm hoping that the volume is turned off because it's just loud. This is a drone. Hopefully that's coming through and not being too sketchy online. And so this is flying. We've got one camera looking at it. You can think of this as an application where you've actually got 2 vehicles and they've got a camera on each, and one of them is trying to figure out the position and orientation of an object so it doesn't run into it. And this is, I think, not an atypical situation. You've got this little black drone flying around. It's got things in the room that are hard to see. But imagine this also outside, because there's all kinds of issues with drones flying around, commercial aircraft. There isn't any way of tracking them. And, there's all kinds of incidents. If you look at the reports, there's dozens and dozens of incidents these days of drones at commercial airports. And if you suck one of these things into a jet engine, it's not going to be a good day. So thinking about how could we find them if they don't have transmission information on them. So if you look at this, one of the things we looked at, so we did, I'm going to, again, kind of put a bunch of stuff under the rug here. But so we looked at using neural networks to classify the position and orientation of the drone based on, training from a whole lot of data. As you might expect, and I think I just didn't put the slide in here, doing that in a discriminative sense. So just, doing classification without putting any kind of physics or Bayesian information in there from like a generative point of view, it jumps all over the place. And so that's sort of this picture on the left. Let me run that again. Put that on loop, sorry. So this is the result. I guess it's not so easy to see in the picture. What we did was we took this and said, okay, well, let's apply some physics, put a filter on it. It's sort of along the lines of physics-informed neural networks. It is not officially a physics-informed neural network if you aren't familiar with such things. But we just put a Kalman filter. We piped the image information out through the pose information through a Kalman filter. And if you look down here, so these are the results here of doing this, and I'll connect this back to the observability in a moment. You get better results, not surprisingly, by pushing it through the Kalman filter. So the error goes down, but also the error covariance tightens up quite a bit. So the green dash line here on the top one is for just the neural network. And then if you add the Kalman filter onto it, it tightens up quite significantly into that blue one. Okay, so what are we doing that's more aligned with the tools from the observability for these kinds of neural network applications for pose is looking at, can you use this observability information to help drive what views are good? So, go to the good views if you're trying to classify something, or if you need to gather more information, like more training data, where should you go? Like which poses or what camera placement should you use to get better information? So we did a bit of a study using Blender, just using constructed data. So again, this was not physical data. This was just done in Blender of a camera view of different objects. This one was a bicycle, and then looked at using different of the metrics. So the things here. So the black line is a neural network classifying each of these poses, orientation specifically. How well the neural network did compared to the empirical gramian version of what is observable, and using different of those metrics. So one of them was the determinant of the gramian, one was the trace, and one was minimum eigenvalue. And so you can see how those kind of played out in terms of the different orientations of the bicycle. And this kind of holds for different kinds of objects as well. And so there is this relationship between these gramian studies and, of course, like how the neural network was able to perform, with the upshot being, you would want to avoid camera being pointed at the object from this location, like head on or tail on, in terms of trying to do classification of pose. And we can relate. So I do want to make a point about this. So I mentioned sensitivity earlier, which was the sensitivity of your measurement function relative to the state of the system. The term sensitivity is used a little bit differently in neural networks. So I just wanted to put this up because honestly, I started doing this just for myself so I could keep my own language straight. So I thought it was good to put it up. So in systems theory, the pose is your state, and your measurements are coming from your navigation system, and your sensitivity, what I had shown before, is the relative information from the measurement to the state. And so unobservability is when that sensitivity is 0. Observability is good when it's greater than 0. The answer is a bit different when you think about sensitivity from the neural network point of view, which you have your measurements are Y, the classification value is Z, and the sensitivity is DZ, DY. And so when we think about observability, just bear in mind the math is a little different. But we've done some work around this, classifying like how well you can do with sensitivity in neural networks. Yeah.
The state is the viewpoint, I suppose, and the observation is the network's answer.
Yeah, so the state in this particular situation is actually position and orientation. In this particular plot, it is the orientation. And the measurement was actually the image of the object. So like the full, like assuming you had a camera image and so it was trained on a whole bunch of data. I don't even remember how much data off the top of my head. Sorry. It's
So the network was trained to classify, yes. I was wondering how the gramian was calculated.
Oh, so the gramian was calculated by what we did was we took each of the images, like we did some blenders, we took the bicycle and we did this at a whole lot of positions. I don't have the best picture here, but so we took like, imagine like a dome around the bicycle image, put the camera at each position. From the training data, we perturbed the camera position plus or minus epsilon, like in its view, and then used that, like in that whole empirical gramian, we used that to
So I guess it's
do the trajectory. I'm sorry, it's actually been, I'm sorry, I wasn't anticipating that question. It's been a little while since I did that.
Perhaps it's a single step calculation, not a dynamics of these.
I don't think it was dynamics. I think it was a single step or at least a small time horizon. I mean, there was still a trajectory in there, but it was a small one.
Okay, that makes sense.
Yeah, yeah. We had to get a better computer for that one. We didn't go so far as like a cluster situation, like high performance computing, but it was working a lot. Yeah. Bottom line, doing anything with vision is highly computationally intensive. Okay, so going back now, switching gears again a little bit, I'm going to bring back in some of the stochasticity that was mentioned earlier. So key thing about any of these tools that I've shown so far, and honestly what people use in general, observability is done as a deterministic assessment. So even if you have a stochastic system, the calculations, like if you go back to the kind of classical observability matrix for a linear system, which is CA squared, that matrix, there's nothing in there about noise in the system. If you're doing this in like the nonlinear tool set, again, you take off the noise and you just do the calculations on the deterministic part of the system. However, estimation filters are constructed in the presence of noise. So like when you write down a Kalman filter, like it doesn't make any sense to do it unless, I mean, it assumes in like the gain and everything that you're factoring into it, the noise terms. So comparing tools, apples to apples gets a little more challenging unless you do observability from a stochastic point of view. So we have done a little bit of this. There are not a great number of tools for stochastic observability. I'm just going to give the one that we have been working with, which start with your stochastic system up here. It turns out you can generalize the observability gramian things we've been doing by particular structure. This where our trajectories are going to be the same kind of thing, plus or minus epsilon. But now your initial conditions are going to lie in a probability density function, which allows you to get some of that stochasticity in there. So I did, this is an example here of just your basic unicycle system. So Dubin's car, however you want to call it. It turns out, and this actually was the question we were asking here, is in a system with noise, if it's a system where you know that you need particular control in order for it to be observable, so if you go back to the analytical tools for the deterministic systems and you need it to be moving in a particular way, such as like the airfoil vehicle, the question was, is it possible that the noise in these systems, the inherent noise that's actually already there, is that perhaps actually providing sufficient excitation to give you that observability result, even without doing anything else? And so short version is yes. And so this Dubin's vehicle, we were able to show that if you have sort of like just generic noise in the system, and I don't remember what the parameters were, sorry, I should look that up. As long as the system is moving, there is enough noise in there to provide the excitation that's needed in all of the directions in order for the system to be observable. So there's a lot more that can be done with this. It was just a very particular simple result, but where we think that we can go with this is doing a hybridization of physical data with empirical data. Because, so in physical systems, if you go back to exactly what was asked about the trajectories, the calibration of everything, the tools that we have for the observability gramian, say the empirical observability gramian say you have to perturb exactly by plus or minus epsilon in each of the basis directions. In a physical system, you're not going to be able to do that. The best you're going to be able to say is I got it as close as I could, and it's kind of this close. And so you could then describe your initial conditions and their perturbations with a probability density function. So now we think, we haven't gotten so far as to doing this, that you could take physical trajectories that start sort of nominally in a particular place and then augment those with generated trajectories and build out a stochastic empirical observability gramian and get information about either is the system going to be able to provide the information you need, or are you going to need to gather additional information? The example I'm showing here, this is actually from a FedEx. I love this particular video because it's FedEx operating in a storm around a thunderstorm, which happens out there. Yes.
I apologize. I don't want to be controversial, but I am taking issue with your definition of observability.
Okay.
Okay. Observability is not the physical reality. It's only a reflection of the physical reality
Oh, absolutely.
because of the transduction.
Yeah, absolutely.
But your statement was much stronger.
Okay.
Okay, and that's what triggered me to take an issue. If I remember, you said, I forget, observability is the detection assessment. I guess, can you go back to the first definition
Sure.
when you started with the issues?
Like here,
Yeah, before,
before that,
one more.
this one.
Yeah,
Oh, sure.
well, is this the
Or,
one more, maybe?
well, so this one I was just talking about examples of where we're doing things.
Okay, well,
This one was like just, some of the
I
questions.
missed it, but any case, it is really not the reality. And this is the dangerous thing about all this great belief in
Yes.
AI.
Absolutely,
and
absolutely.
And the data.
Yeah,
And the data very much depends on the transductor.
absolutely,
Realistically, how veritably
absolutely. No, I don't disagree at all.
affects the reality.
Yes, no, absolutely. So I think the difference between what I'm saying and
Please emphasize that because
Yeah.
there is a myth.
absolutely, no, I 100% agree. And this is, yeah, I would like to be able to get that message across.
From the National Academy of Medicine, and in the medical area, this myth is so dangerous.
Yes, no, I 100% agree. So let me frame it this way. So when I'm talking about like the observability tools, this is from the mathematical control theoretic point of view, which from a mathematical definition, observability means that you have this, which is deterministic in general, and that this result, like when we say observability, you can extract from the measurement the state. In reality, you never have a deterministic system. And so what people, I 100% agree that when people are saying like, I can extract the state from the measurement, and I'm going to call that observable, technically, I mean, that's not the same observability that I'm saying here with these mathematical tools. That is more of an implementation. Like, can I physically in the real world do that inversion and know that it is correct? And that is absolutely a very different thing. Yes. Yeah, no, I don't disagree. And that's I think where there is a lot of, language that one of the things I love collaborating with people. And I've worked with biologists and various people from like the beginning of my education. One of the hardest things is to get everybody on the same page on language. I distinctly remember a conversation with one of my fish biology colleagues where we were talking about some of these models of schooling fish, like how they interact with one another. And what she meant by like an elastic interaction was the opposite of what we mean from like a mechanical engineering point of view. Like it took like hours to be like, wait a minute, write down what you mean math wise. And it was like, oh, that's not the same. Yeah. So it's vocabulary matters hugely. So does punctuation. I'm just thinking like I have this t-shirt I got from my husband and my son that says, it's like, it's a dinosaur and it's the one that says, let's eat, comma, kids, let's eat kids. Punctuation saves lives. I have a 13-year-old, so he is less interested in commas than I am. Anyway, so one of the applications here, and I do realize I'm up against the clock here. So this one, I just like this one. I'm not going to play the video, but this, so FedEx, if you've ever seen the videos of their fleet taking off at 2 a.m. out of Tennessee, I forget exactly where in Tennessee. I don't think it's Knoxville. Can't remember where their hub is. When they run up against a thunderstorm, it gets super exciting and they have to navigate around it. And so from an observability, like a physical observability point of view, it's like, where do you know the weather well enough to steer around it and what it's going to do over time so that you can like do a prediction of the weather in some sense, so that you can get most efficient pathways to go around it. But there's this one video, it's super fun because they were actually telling us when we were talking to them that like there's this one pilot who likes to go into the thunderstorms. And so you see this one rogue like airplane in the thing, like doing weird things around thunderstorms. Don't recommend it. Okay. I don't think they actually really like it, but what do you do once they're up there? Okay, so just as a summary here, so there's a lot of open territory of things that can be done, both with development of these tools from a mathematical point of view, but then also with applying them to different kinds of systems. So some of the key things that we're really looking at in my group right now is, I didn't talk at all about really how do you select a good nominal trajectory. So like you've done the empirical observability gramian, you assumed a particular trajectory. How do you know that that one was going to be the right one to check? What do you do when you have limited data situations? So like upper atmosphere, we don't have a whole lot of data about the upper atmosphere. I will also say like a lot of the data that we do have is military, and we do not get to put that into models in the general public. Undersea autonomy, so also not a lot of data underwater relative to how much data is typically used in models. How do we work with infinite dimensional systems? We have done some work in this area. I didn't show any of that. We're looking at doing active flutter suppression. So how do you do sensing on an aircraft in order to do the best control for gust situations or flutter suppression? And then what do you do when you're in a resource constrained real-time implementation? So like animal flight, robust animal flight, like what do you do there? So using elementary sensors, things like that. How do we make that kind of tool work? All right, and just my acknowledgement slide. So this is the number of my students who, of course, made this all work. There's no way I could do all this. And then a bunch of our funding agencies over the last several years. And with that, I will end and take any questions, take more questions.
If you're online, please remember to post your questions in the Q&A.
Thank you for your talk. I have a question about your project where you put the different IMU sensors on different places on the plane.
Yeah.
And then you were able to resolve the inertial properties of the plane. What other inputs were there? Because I'm struggling in my mind to figure out how motion information from IMUs can discern like even just the scale of the mass and the center of mass. Like, are you including sensors from the other or information from the other sensors?
Yeah, so just first of all, full disclosure here, none of the data I showed are from Boeing. Just make sure we're NDA compliant here. So the information we get is translational acceleration. So this is a planar model. You could do it in 3D, it's just harder. So forward and sideways, forward and up translation, and angular velocity, so pitch velocity. So those are the three things we're measuring. And because of this is nonlinear dynamics. So because of the coupling of the dynamics, I didn't put them on here, but because of that, just having that information is in fact sufficient. As long as you put sensors in appropriate places and run an appropriate filter, you can actually get out of that all four of these, that's not the right plot, this one. All four of those.
But do you have like a dynamics model?
Yeah, yeah. Oh, absolutely. It's a
Okay,
dynamic
makes
model.
sense.
Yeah, yeah, yeah.
Thank
Sorry.
you.
Yeah. Almost all the
Thank
things
you.
I do are with dynamics.
So I was interested in the sensor optimal placement, right? So in the biological system, is there an understanding of, the additional sensors in terms of is it a notion of redundancy? Is it, something else? And if so, can we also optimize over that?
Yeah. So
Criteria?
from my understanding, again, I'm not a biologist. They have, let me see if the picture has like, that's not the hawk moth. Let's go back up. So they have, I'd say, so it's an open situation. Like they don't exactly know what all is going on. I mean, the insect has vision, it has, strain sensors. The question was sort of like, what could they do with those strain sensors? We don't really know. Like the only way you can really know, and I don't think these studies have really been done, is like to ablate the sensors and then see if it can still do the same task. That's the thing about biology. So the problem is here, if you ablate the sensors on the wings, you probably destroyed the wings and then it's not really clear. So it was really more a question of like, is it possible that this is what's going on? Because I mean, we know that they don't have an inertial measurement unit. Like some of them, like some kinds of flies, I mean, to a certain extent, this is present in all of them. They have this hind wing. So like a crane fly has this vestigial hind wing, which is basically turned into a proof mass on a rod. And so when the wing flaps like this proof mass, and so then you're kind of, well, maybe it does actually have an IMU on it. But these don't really seem to. And I think the key thing with insects and most biological creatures, they have so much redundancy. And I think that's because things break over time and they don't get new sensors. It's not like they usually grow new ones. So it's just interesting to see like what could be done with those. So a lot of these studies are being done with biologists informing like what questions could they then ask? Yeah, so we don't really know. Yeah.
Thank you. I was wondering on the same topic, in the optimization objective that you wrote down there, is there a notion of a cost associated with each sensor? For example, in the case where you have, as you go down, you want to maximize the load, which would be, I would assume, monotonic. You would add all the sensors.
Yeah.
All the sensors were represented by these switches. You would just have all ones being the best. So there must be some kind of trade-off.
Yeah. So because it comes out, what we did, wrong way. We just decided, we haven't pushed it too much further than this to add like basically you're saying add another cost for cost of sensors. Yeah. We just decided to put a limit on it. Like, so we know that there's 200 on a wing and that clearly that's a lot. And we don't think that they're all like active at the same time. That is one of the questions the biologists are looking at, is like trying to get measurements of the spike patterns. Like you have to be able to get into the nerve bundle and figure out like what's spiking. So we just said like assume that there's like 20. So we just artificially chose a number, and so like this one was done with 20. Oops, next page. And then I think like some of these, yeah, I think they were all done with 20, but we did it with different numbers. No, so the number, so we said 20 total, whether they came out as bending or shear. I will say that like the bending come out first. And I think that's just because like the root of the wing, like you get really good, strong information there. But as you added in more, I think we went to 20 because it took a while to get some shear ones showing up. But yeah, that is another thing that can be done. Mm-hmm. Yeah.
We have something else scheduled in here, so we can't keep going. So thank you. Let's thank Professor Morgansen one more time. So as a reminder, you can find today's talk and previously recorded talks on our YouTube channel and website. Next week, please join us at the same time for our next Grasp on Robotics seminar. And we're featuring Professor Marco Pavano from Stanford and NVIDIA. So for more information on upcoming events, be sure to follow us on social media or check out our website. Thanks and have a great day. Okay. One more thing for those of you who want pizza. Pizza today is being served in the grass